Hi, so my name is Andrew Fleck, and the title of my talk is With or Actuarial Science. So as a disclaimer, I should probably say I'm not an actuary or an actuarial scientist myself. I'm a PhD candidate in applied mathematics at York University in Toronto, Canada. And I'm loosely affiliated, however, through some members of my committee with RISC, which is the Risk and Insurance Studies Center. And this is a group of people who try to study insurance risk from a kind of interdisciplinary perspective, touching on statistics and economics. And hopefully by the end of this talk, I'll have convinced you that ergodicity economics is another topic with fertile ground for research and connections between these two subjects. So after a short introduction, I'm going to talk about two examples, one involving a non-life insurer, the other an investment consumption problem. And hopefully by way of these examples, show that there's a sort of duality between actuarial science principles, in particular Ruin theory, and ergodicity economics. So there's already obviously been some work in ergodicity economics related to insurance. The Peters and Adamou paper from 5 years ago, Insurance Makes Wealth Grow Faster, solved the so-called insurance puzzle under the assumption of multiplicative wealth dynamics by showing that both parties would voluntarily enter an insurance contract because it increased the time average growth rate of their wealth, right? So what they did is they interpreted insurance through an ergodicity economics framework. And what I'm hoping to do here today is actually kind of the opposite. I want to look at ergodicity through the lens of actuarial theory and practice and see if there's any connections or conclusions we can draw. So starting with a non-life insurer, we can model using this very classical Kramer-Lundberg model, the surplus for this company, right? This non-life insurance company. We start with a starting capital. We charge it some premium rate through time, P, that gives us our revenue. And we have losses that come in with at a compound saw process with rate lambda. And we're going to assume everything is nice, right? So our individual losses or XIs are not going to be fat-tailed or anything like that. And we're going to go ahead and define the ruin time as the earliest time such that the surplus slips below zero. And we're going to define the probability of ultimate ruin as the probability of this occurring over some infinite time horizon. So if that number is very low, right, if your probability of ultimate ruin is negligible, then you can be pretty sure your insurance company is safe. So calculating those probabilities themselves, though, are very difficult. So we typically have to use heuristics to come up with results. The first one is this net profit condition, right? And basically what this says is that if our premium rate is lower than the rate at which losses come in, then obviously we're going to have ruin with probability 1. So we can't have this. We have to have it be greater, strictly greater. So in order to do this, what we typically do is add a safety loading. So we charge the rate at which losses come in and then add a little bit. And so it was observed in the Peters and Adamou paper that for large wealth, so for large surpluses, this net premium was often charged. That is, there was no safety loading. And the reason for this is that it's usually implicit in these models that the force of interest on our surplus alone is enough to provide a safety loading. But we're not going to consider interest rates here. Another thing we can do, another approximation we can make is use this Lundberg inequality. So we can actually bound our probability of ultimate ruin by a nice exponential function, as shown here, where the coefficient is given by this equation involving the MGF of our ultimate losses. And so what we can do is we can be very clever and we can say, I want to cap my probability of ultimate ruin at some negligible number epsilon. I can invert this inequality and use the definition for R and come up with this nice premium calculation. And if you notice, for those who know, this is also the entropic risk measure, or what's sometimes called the exponential risk premium, because it's the certainty equivalent under an exponential utility function. So there are other ways, obviously, to calculate premiums, but the important point I want to make here is that this is a way of making decisions that has an operational and time-based interpretation, right? So in much the same way that utility functions in ergodicity economics are interpreted as growth rates, right? Our premium calculations are interpreted in terms of an operational criteria that acts on the individual over time. And in this case, it's ruin. And so we've removed any kind of subjectivity, right? So the only kind of subjectivity here is tolerance for ultimate ruin, not some kind of idiosyncratic psychology. But of course, we're here to talk about ergodicity, so let's try and make a ergodic interpretation of this. So in this framework, we say that agents maximize growth rates. And the next question is then, well, what is a meaningful growth rate? Well, the meaningful growth rates, according to Ergodicity Economics, are the ones where if we have this mapping new, right, they satisfy this property where our time average growth rate is going to be equal to our ensemble average locally. And so in our case, in the Kramer-Lindbergh model, we're lucky because we essentially have additive dynamics. So we can just take nu as the identity function and show that our time average and our ensemble average are both just our premium rate minus the rate at which losses come in. So our net profit condition, which said that this quantity had to be greater than 0, has an ergodicity interpretation, which basically says that in order to avoid ruin with probability 1, we have to have positive growth rates. So this makes sense. But what we're really interested in when it comes to the insurance puzzle is sort of an equilibrium framework, right? So to that end, what I'm going to do is I'm going to set up a very simple model. I'm going to consider n individuals or companies that have the same form as my insurance company, right? So I'm going to start with some wealth, I'm going to earn some income, and I'm going to be exposed to some losses. But now the losses are going to come in at a lower rate. They're going to come in at lambda over n. We can imagine that these companies or individuals would want to pool their risks together with some insurer, and that they would probably be charged some premium rate, let's say P over N. So if our insurer starts with the same initial capital, U naught, then clearly we can recover the Kramer-Lindbergh model in the dynamic for the surplus we had earlier. And now what we can do is we can compare the companies and the insurer without coverage and with coverage. So without coverage, we know that the companies have some positive growth rate, right? And the insurer has none. They just have some money. With coverage, the companies still have some positive growth rate, assuming that our premium rates are reasonable. And the insurer also has a positive growth rate. Now, the catch is that in order for the insurer to enter into this, the net profit condition must hold. So this P minus lambda expected value of X has to be greater than 0. But if that's true, it means a decrease in the growth rate for the company, people entering into this contract. However, I would point out, these companies before coverage had a non-negligible risk of ruin, and now they have none. Whereas the insurers have taken on a risk of ruin, but because of their large starting capital, and this is often required by regulatory bodies, they have a negligible risk of ruin. So in the case of the net profit condition holding, what we're seeing here is that the growth rate of these companies would be lowered while the insurers would be increased. So it seems like there's kind of a zero-sumness. And of course, the insurance puzzle pops up again. This question exists. Why would insurance exist? Why would these companies enter into this contract? And I would point out that for a large amount of companies, for a large N, this decrease in their growth rates is negligible, but the coverage eliminates a non-negligible risk of ruin. And the insurer achieves a positive growth rate at the cost of a negligible risk of ruin. So I would conjecture that maximizing growth rates is less consequential if you seriously face ruin. And minimizing ruin is useless if you can eventually be outgrown by your competition. So trading off ruin and growth rates can probably be beneficial. To see this, let's look at a different example. One that maybe we're more familiar with, investment and consumption. I'm going to consider a framework we're all well acquainted with, which is an investor who has a bank account with some interest rate R and a risky asset described by a geometric Brownian motion. And I can come up with a control variable F, which is the fraction of my wealth invested in the risky asset. Now the difference here is I'm going to add a possibly non-trivial consumption term. The question is, what is the optimal F? If there is no consumption, right, then this is easy. Our growth optimal strategy is what we usually call the Kelly criterion, right? So we have logarithmic growth rates that are meaningful. These are ergodic observables here. And we can also, using some known results, find our ruin optimal strategy, which is going to tell us that we don't do anything, we don't invest in the risky asset at all if we have positive interest rates, because we can just earn a force of interest. Or if we have some kind of depreciation, that is negative interest rates, we have to bet some fraction of our Kelly. The interesting thing happens, though, when we add a non-trivial consumption, because before asking what the meaningful growth rates are, we have to find our appropriate nu. And we have some nice conditions provided for us in the time interpretation of expected utility paper provided by Peters and Adamou a few years ago that restrict what cases can have a meaningful ergodic growth rate. So their equation 27, when you apply it, puts some restrictions on what the form of f can be. So a constant f, if you apply this, is automatically ruled out. And to me, it seems likely that no dynamic f of x, that is a fraction that responds to our total wealth level, is permitted either. You can find an ODE, but it's not clear to me that meaningful strategies actually exist. So if someone else wanted to take a look at that, perhaps they could find one, but so far I haven't been able to. We can, however, calculate our ruin optimal strategy, right, given below. So what this strategy is telling us is that we have to bet smaller and smaller fractions of our Kelly criterion until our bank's force of interest is enough to cover consumption. Now, to me, this seems incomplete because once we've reached that point, right, then we could take whatever excess we have and we could finance a self-financing portfolio, which then does maximize growth rates. And to me, this is reminiscent of Taleb's barbell, where you cover catastrophic loss and then you take on risk as you please, right? And so this suggests to me a bit of a bigger universe exists here. And so I want to leave you with these thoughts. I'm not suggesting that ergodicity economics and actuarial science are in tension or contradicting each other. In fact, I'm saying the opposite. I'm saying they fit within a more general theory of decision making. And this just general theory central insight is that we must consider a single individual through time, right? And that potentially including the risk of ruin may help in the design of future experiments, a la the Copenhagen experiment, where perhaps a risk of catastrophic loss would see us test the limits of ergodicity economics and see where they give way to maybe some kind of ruin consideration. So thank you for your time. Special thanks to the London Mathematical Institute for organizing. I'm going to include here a couple slides with the references I just made, and I'm looking forward to speaking to you all. Happy New Year.